Today we want to look at some questions from the Momentum and Collisions homework. We're going to look at questions 13, 14, and 15, and I want to give you some hints about how to work those. I don't want to work those out for you completely in this session. I just want to talk with you and give you some helpful ideas and maybe help you to think about an approach that would allow you to really work with those and see if you can work those out on your own. All right, so number 13, we've got a student, and we are given the student's weight, and he's in the middle of a frozen pond, and we're given its radius, and he's unable to get to the other side because there's no friction between his shoes and the ice. All right, and clearly we're in desperate times because he is willing to throw his physics book. He's willing to depart with his dearly beloved physics book in order to try and escape from where he's trapped in the middle of the pond. All right, and we're given the mass of the book. Let's see, and we're told then that he's going to throw the book horizontally. All right, so what we've got is we've got a pond, and this student is trapped in the center of it, and he's trying to get to the other side. And what we have here, we have two things that are going to happen. He's sitting in the middle of the pond, and he's holding his book, and then he throws the book one way, which, of course, is going to propel him the other. And so what we have here is we have a separation event. And since we're in a situation where there's no friction and there's no other outside forces, then the conservation of momentum is going to apply. And so the initial momentum and the final momentum of the student in the book will be conserved. All right, and so now, of course, initially everything's at rest, and so we know that the initial momentum is going to end up being 0. And that's how we know then that throwing the book one way will cause him to travel the other. So before we've got the mass of the book, we need the mass of the student. Well, we're given the weight of the student, but you can find the mass of the student from the weight, and so you'll go ahead and find that. And at that point, then you'll have the mass of the book, the mass of the student, and we know that everything's at rest to begin with. But then afterwards, we're told that the book is thrown with a certain velocity. And so that is actually going to be VB prime or VB final. And so you have the final velocity of the book. And by using those along with this idea of 0, you will be able to then, so you'll be able to use these three things along with your conservation of momentum and your conservation of momentum equations from your notes and from class, and you'll then be able to find the final velocity of the student, or Vs prime. Well, at that point, once you know Vs prime, you know the radius of the pond, and that's how far he's going to have to travel. So that's actually then delta x, and we will use then, knowing the velocity of the student along with delta x, we'll be able to use those two things to find the time that it takes him to reach the side of the pond, and that's what we're really after. So again, this will start with a conservation of momentum idea and a separation event, and then we'll use the information that we gain from that, specifically Vs prime, and we'll use that, and then we'll use some of our old kinematics skills from our very first unit, and we'll use those then to find the time. Okay, and remember that since there's no friction, that is an initial velocity, a final velocity, an average velocity. It will serve as all of those velocities. Since there is no friction, there's no force on him, there's no acceleration, and so the velocity is constant the entire time. All right, so that'll be all we'll say about that for now. Hopefully that will be enough to get you started. And then let's look at number 14. We've got an experimental dart which is fired into a block of wood, and of course once it does that, then it sticks in the wood, and then it travels off of the wood in a parabola projectile kind of path. And so what we have here in this case is we've got first where one object strikes another object and they stick together. Hopefully you're going to recognize that as a perfectly Oops. Let's change that back to a solid text. There we go. And so hopefully you're going to recognize that where the dart strikes the block and sticks together, hopefully you're going to recognize that as a perfectly inelastic collision. Okay? And when that happens, of course, momentum is conserved. And so once again, we're going to have our initial momentum is going to be equal to our final momentum, and that's going to be for the striking of our block right here. At that point, then they're going to depart as one collective unit, and they're going to travel off of an elevated surface and fall, again with no forces in the x direction and gravity acting in the y dimension. And so that then will be projectile motion. And so we'll be using our old projectile motion ideas. So we'll have a perfectly inelastic collision, and then we'll use projectile motion in order to solve this one. Okay, so let's look at our givens and see. All right, we're given the see, we're not given the velocity of the dart. We're given the mass of the dart, and we are given the mass of the block of wood. So mass of the block. And of course the block of wood's initially at rest, and so we have that. And then we're actually looking for the initial velocity of the dart. That's our question that we're after. So these two things we know, and we're looking for the velocity of the dart as it's traveling before it strikes that. So that'll be the initial velocity of the dart. All right, and then it strikes the wood, and so since it's projectile motion, we'll work those in our x and y dimension. And let's see, we're told the height of the post, so that means we know delta y because we know how far it's going to fall toward the ground. It's under the influence of gravity, so we know the acceleration due to gravity. And remember that as they depart straight off the post, that will be an initial velocity in the x dimension, which we don't initially know, but we do know then that the initial velocity in the y dimension is 0 meters per second. And so we have delta y from the height of the post, we have the acceleration due to gravity, and we know that the initial velocity in the y dimension is 0. And using those three things, we can find time. Now let's see, we're also told how far away it lands. And of course that will be delta x. And so we know delta x then, and so once we know delta x and time, remember that we can swing time across here. Once we know delta x and time, which we'll solve from our y dimension, once we know delta x and time, well then we can use that to solve its velocity in the x dimension. In other words, we can solve for how fast it was going when it left this post. And the neat thing about that is the velocity that it has here, sort of that initial velocity for the projectile motion part, is actually the final velocity from this perfectly inelastic collision. And so remember, if you look at the equation for your perfectly inelastic collision, the two objects end up having one common velocity after the collision, and it turns out that that velocity is actually the same as this x velocity right here. And so the velocity in the x dimension, which we'll find through these steps, then turns out to be v prime from our perfectly inelastic collision. And so we'll take that value, which we found from Vx, and we'll swing it over here and use it along with our masses and the initial velocity of the block, which is 0. And so we will use those two things then to solve our perfectly inelastic collision. And we will solve then for the initial velocity of the dart. And yay, happiness, declare victory. There it is. All right. So again, the y components to find time in the x dimension to find initial velocity of x, which also happens to be the final velocity from the perfectly inelastic collision, and then substitute that in with our initial givens in order to solve for the initial velocity of the dart, which is what we were really asked for in the first place. By the way, I noticed that in this case the masses are given in non-standard units of grams. Don't forget to convert those to kilograms before you begin, otherwise you will not be able to solve for a correct solution. All right, well that's going to take care of that one. Let's go. Let's go then and look at what we've got. A perfectly inelastic collision again. So this time we've got a bullet that's fired from a rifle, which then strikes into what's called a ballistic pendulum. And this is just a block of wood or plastic or some other soft material that the bullet could embed in, and it's a pendulum, and so it is suspended from two strings. And of course, when the bullet strikes it, that's going to give it a certain amount of velocity. It's going to give it a certain amount of kinetic energy, and it's going to swing like a pendulum. And so that bullet embeds in the block swings, and it's going to swing to a particular height, h. And when it does, what we're going to do here is we've got our bullet embedding in our block, again, two items becoming one, and so again we've got a perfectly inelastic collision. But this time, instead of that going into projectile motion, it swings up as a pendulum, and so at that point then we're going to be able to use conservation of mechanical energy, because this occurs without friction, and so we're able to use conservation of mechanical energy. In other words, the initial mechanical energy here at this point is going to equal the final mechanical energy at this point. Remember that our initial mechanical energy is made of GPE and KE. Ooh, the K is having a bad day. So our initial gravitational potential energy, our initial kinetic energy, and those will then also equal our final gravitational potential energy and our final kinetic energy. Well, if we look at this and if we treat this as our reference point, then the initial GPE would be 0, and we would have our initial kinetic. And then here we'll have some final GPE because it's elevated at a height above our reference point. But it comes to rest at the peak of its flight, and so the kinetic energy final is 0 joules. So at this point we can see that our initial kinetic energy is equal to our final gravitational potential. Well, since we have the mass of the block and the mass of the pendulum, don't forget to combine those since they are combined from this point onward. And that I'll just call our mass total. Since we have our mass total and a height, and we know g, we can find the value for GPE. And again, since we know our mass total, we could actually use that to solve for our initial kinetic energy, our initial velocity. And so we'll solve again for our initial velocity here from our kinetic energy formula. And it turns out that the initial velocity of the swinging kinetic energy part is the final velocity from our perfectly inelastic collision. And so once again, with our perfectly inelastic collision, where we know both masses, we know that the pendulum was at rest. The pendulum block was at rest initially. The bullet has a certain, again, grams. Don't forget to convert that right away to kilograms. But since we know that this was initially at rest, since we have both masses, and since we now have a final velocity, you'll be able to use your formula for your perfectly inelastic collision and solve for the initial velocity of the bullet. All right. I hope that was helpful. Just a few hints to get you started. And again, if you'll watch the sections that you need as often as you need to, and look at those along with your notes and along with the rest of the formulas in there. I didn't spell it all out for you, but you can look in your notes and find those formulas, and you'll be able to come to a solution. I hope that's helpful, and wish you the best of luck. Thanks for watching.